This is the first in a two-part series looking at how equilibrium systems respond to change using what's called the Chatellier's principle. In this video, we will be primarily focusing on the effects of altering concentrations on equilibrium systems. Le Chatelier's principle is essentially a way of viewing equilibrium systems and predicting the change that will occur when we perturb the systems. So once a system is at equilibrium, the concentration of all the reactants and products will remain the same. This equilibrium is dynamic, so the reactants and products are continuously switching between themselves, but the concentrations of them will be the same. If the conditions are changed, the concentrations of all the chemicals will change until equilibrium is restored. So if we alter the concentration of one component, it will cause a shift in the reaction that will lead to different concentrations. However, over time, equilibrium will be restored. And so the ratio of products over reactants raised to their respective powers will result in the same number. The new concentrations will be different, but the equilibrium constant will be the same. That is, unless you change the temperature. So as long as we do not change the temperature, the ratio of products over reactants raised to their respective coefficients will be that same equilibrium constant. The actual concentrations that we are plugging into the equation will be different, but the value of the ratio will remain the same. This follows along what we will call Le Chatelier's principle, which says that if a system is at equilibrium and it is disturbed, the position of the equilibrium will shift to minimize the disturbance. It gives us a guide for predicting the effect of various changes in conditions on the position of equilibrium. So for example, we could add one of our reactant components, thus increasing the concentration. So if we look at Q and compare it to K and how we are affecting both via changing the concentrations, let's say we have a reaction A of A plus B of B goes to C of C plus D of D. If we have a system that's at equilibrium, Q is equal to K. If we take and add one of our components, so let's say we take and we add some of this C, the concentration of C goes up. The system is no longer at equilibrium. The value of Q would be greater than the value of K. If C goes up, we have a larger numerator, the same denominator, but if the numerator is larger, our value for Q will go up. It is now no longer the same as K, and so the reaction must shift to re-establish equilibrium. Remember that if Q is bigger than K, then the reaction will shift to the left to get rid of some of your products and form some of your reactants. A key part to remember is that changing the concentration does not change the equilibrium constant. It will lead to a change in the equilibrium concentrations, but it will not change the equilibrium constant. Another thing that we could do is remove one of our components. So let's say we remove some B. So if we pull out B, one of our reactants, perhaps via a secondary reaction that precipitates or removes it, if B is being removed, then the value of the denominator here decreases. If this decreases, then that means the denominator goes down, our overall value goes up, and Q is again bigger than K. So the reaction would need to proceed in such a way to reduce the value of Q. So the reaction will proceed back to the left to produce more B. Essentially, Le Chatelier's principle says whatever you do to the system will try to undo it. So if we add C, the system will try to get rid of C. If we remove B, the system will try to make more. If we remove D, the reaction will shift to the right to make more D. If we add more A, the reaction will shift to the right to try to get rid of some of that A that we added. Whatever you do to the system, according to Le Chatelier's principle, a system at equilibrium will attempt to undo the change that you made. Let's now look at a couple examples. So let's say we have a system that is a mixture of N2O4 and NO2. And we're going to say that it is at equilibrium. So if we are plotting concentration versus time, in this region here, we are at equilibrium. We will then spike our reaction vessel with some N2O4 at a particular time. So it instantaneously, because we're dumping a bunch of new N2O4 into our container, it will instantly jump up. So we are taking and we're adding a reactant. But after that initial spike from what we added, you'll notice that the concentration of N2O4 decreases from where it was following the spike. So the concentration will go down. As the concentration of N2O4 decreases, you'll see that the concentration of NO2 increases. So what this is telling us is that if we dump in some additional reactant, the reaction will shift to the right to make more product. So our concentration of NO2 goes up, our concentration of N2O4 goes down. The values that we are left with when it reestablishes an equilibrium, and we can tell that it's reestablishing an equilibrium because the concentrations level off. So when it reestablishes an equilibrium having the exact same value for K that it did before and the same value for Q that it had before, you'll notice that the concentrations are different from where they were before. Our concentration of NO2 is greater than it was before, and our concentration of N2O4 is greater than it was before we spiked it with additional reactants. However, it is less than the value directly after we spiked. So right after we dumped in some of our reactants, the concentration went much higher than where it resettles at its new equilibrium. So now if we do sort of the opposite and add some product, we're looking at the exact same system, N2O4 going to NO2 or to NO2. We initially have our equilibrium. We then spike our container by dumping in some product. We are essentially adding in NO2. There's a quick jump in the concentration of the NO2 because we added more of it, and then the concentration of the NO2 decreases and then reestablishes a new equilibrium. As it is decreasing, more N2O4 is being formed, eventually establishing a new equilibrium. The K values between these two are the exact same. The Q values, once you reestablish equilibrium, are the exact same. However, the concentrations that we are plugging in are different. So essentially, what we find is that what we do to the system will try to undo it. Here we added product, the reaction removed product, forming more reactant. In our previous example, we added reactant, the system shifted to form more product, thereby getting rid of our reactant. So Le Chatelier's principle essentially says, whatever you do to the system will try to undo that change.